chapter of moments and forces. We still have only a last section in this chapter, and when we finish, if you have any questions for the exam, we can do them. Okay, so here in the last section, we will learn how to reduce a distributed load into one force. So in many cases, instead of having one concentrated force, we have a distributed load. What we mean by distributed load, it's a load per unit length or per unit area. Okay, so it's like pressure, it's like the action of wind, the action of fluids on a surface. So all of these examples are distributed loads. Okay, so it's often convenient to replace the distributed load with an equivalent force acting at a point such that the moment due to the equivalent force is the same as the moment due to the distributed load. So what do we mean by this? As we have seen last time, we can replace a system of forces and moments by only one force. And we say in this case that we have equivalent systems. What was the condition for equivalent systems? We have two conditions. First, we should have the same resultant force. And second, we should have the same resultant moment about any point. Okay? So let us consider the following example here. We have here a distributed load acting on a surface. As you can see, the load is variable along the surface. And always the unit of distributed load is kilonewton per meter. Okay? Because here it's a linear load. If you have a load on an area, the unit will be kilonewton per meter square. Okay? So depending on the type of loading, or they give it in kilonewton per meter. If they give you in kilonewton per meter, you know that it's given per unit length. So to find the force, you should multiply by a length. On the other hand, if it is a pressure, they give you the distributed load in kilonewton per meter square, and to obtain the total force, you should multiply by the area. Now, here we should pay attention that our distributed load is not constant, it's variable. So if we want to find the total force acting on this line, what should we do? In general, okay, we can divide the force here into several small forces, infinite forces. Because here, look, if I take a very small dx here, this rectangle will represent an elementary force. Why? Because W is in kilonewton per meter. To find a force, you should multiply by the length. Okay? But because omega is not constant, you cannot multiply. You don't have one value of omega to multiply with. So you should do integration. Okay? So here, if I consider a very small element of length dx, here a very small element of length dx, okay, what will be the elementary force acting on this small element? I have at this location w is equal to the height here. The height here is equal to the value of w at this point. So this is wx, okay, and you know that because w is in newton per meter, to obtain the force I should multiply w by the length, which is dx. So the elementary force here is wx dx. Okay? Now, if I want to find the total force, what should I do? I should do the summation, because I know that elementary force is equal to omega x dx. This will give me a small force, which is equal to what? It's equal to the area of this rectangle, small rectangle here. But my distributed load is formed by infinity of small rectangles. Okay? So if I take here a very small rectangle close to it, then another one. So I should sum the infinity of areas in order to find the total force. And this is obtained from mass. We obtain this by integration. So to find the total force F resultant for a distributed load, I should do integral over the length, yani over L, of what? Of omega x dx. Okay. I don't know if you are familiar with the idea of integration, and that integration will give you the total area. You know this property, yes?
Yes, yes.
Okay.
Yes, doctor.
So as a first step,
Yes, doctor.
we can say that
Can
to find the total force, okay, we should do integral omega x dx. Now, if omega is constant, so for example, if omega is like this, it will become much more simpler. Why? Because if omega is constant, then we can say that the total load is omega times L. So it's equal to the area of the rectangle. But if we have a variable function, we should do the integration. Okay? Now, we have found what is the equivalent. Can you please mute your microphone? Guys, please mute your microphones when you don't ask questions. So we found what is the value of F resultant. We still need to find what is the point of application of F result. Okay, so here this is F equivalent, but at which distance we should put it from O? What is the condition to know the distance from O? We should ensure that in the two figures we have the same moment about O. Okay, so in order to find x bar, the condition is to say that the moment of the equivalent force about O is equal to the moment of the distributed load about O. What is the moment? So I will write the condition. So moment of F resultant about O should be equal to the moment of distributed load about O. Now, for the resultant force, what is the moment? If I name this distance d, so if I call this distance from here to here, I want to find what should be d in order to obtain equivalent system. So this is d. The moment of F about O is simply equal to F times d, and here it is in the clockwise. So I put here clockwise. Clockwise, the abbreviation is CW, and counterclockwise is CCW. Okay? Now, I still need to find what is the moment of the distributed load. So, in order to find the moment of the distributed load, I should follow the same analogy I did here. So first, I take a very small element. Okay? If I take a very small element of force here, so this is, as we said, the thickness is dx of this element. So the force on this element will be dx times what? Times the height here, which is omega x. Okay? This will give me df, as we did previously. Now, to obtain the moment of this elementary force about O, what should we do? We should multiply by the distance from O. What is the distance between O and this point here? It's what? Guys, please. في noise من مطرح معين. Can you please mute your microphones?
دكتور
Yes.
سكنت تعملينه ميوت.
طيب أنا بس ما إذا بدكم تسألوا سؤال أو شيء. Anyway, يمكن I should من قبل from the main window حط mute. Anyway. Okay. So here you have that the moment of this elementary force is equal to x. So the distance between the elementary force and O is equal to x. So I can say that the elementary moment dm for a small force, dm is df times x times df. And I can replace df by what? By omega x dx. So the elementary moment is x times omega x dx. Okay? Now, how to find the total moment? I do integration. So M total, M of the distributed load about O is simply equal to the integration over L, okay, of the function x omega x, okay? And in this way, I obtain the total moment. Any question on this? Okay. So let us do a small analysis about the result we obtained. If we look here in the equations, we said that F equivalent is equal to integral omega x dx. But you know from math that when you do integral of a function, what do you obtain? You obtain the area under the curve. So we can use this result that for a distributed load, the resultant force is equal to the area under the curve. So if it's not a complex function like here, we can, instead of doing integration, we can find the area. So if we have, as we said, if you have a rectangle here, for example, a constant load, then the resultant force is equal to the area of the rectangle. If we can have several possibilities of simple geometry, if we have triangular distribution like this, for example, okay, if we have this distribution, a linear distribution, we can divide it into two parts, triangle plus rectangle. So we say that the total resultant force is equal to area of the triangle, area 1, plus area of the rectangle, area 2. Okay, so in general, when we have simple geometries, no need to integrate, we just find the area, and the area will be equal to the resultant force. But if we have a function, w function of x, that is not simple, we can do integration to find the total force. Okay, now if we do the analysis for x bar, we said that to find the point of application of F resultant, we should write the equation that moment created by the distributed load is equal to the moment created by this force. And the moment of the distributed load was equal to integral over L of x omega x dx. So this term here represents the moment of, so this is the moment of the distributed load about point O. Okay, now since this moment should be equal to x bar times F, I can find the expression of x bar. X bar is this moment divided by the resultant force. Now I can replace the resultant force by its value. So I obtain integral x omega x dx over integral omega x dx. Okay, but mathematically this means what? If you are familiar with the definition of a centroid of an area, how you define the centroid of an area? Look, here omega x dx is elementary area dA, because we said that when we do omega x dx, you obtain what? You obtain the area of a small rectangle here. So we can replace omega x dx by elementary area, okay? And then my equation becomes x bar, which is the distance of F resultant to O, is equal to integral x dA over integral dA. And of course, integral dA represents what? The total area. So this term here, which is F resultant, is total area under the curve. So this is the area under the load. And integral x dA represent, if you want here, the moment expression. But from math, if you do integral x dA over A, what do you get? You know the mathematical property to find a centroid of an area. How you find centroid of an area? If you want to find the centroid of area, what do you do? It's if you have simple geometries, you can say that x bar, so x of centroid times A total, equal to summation of xi ai. Okay, what do I mean by this? So for example, if you have here, if you have a rectangle and a triangle, and you want to find what is the centroid location of this geometry, what do? You divide your geometry into two parts. This is part one, this is part two. If you want to find x here of this in this figure, what is the location of the centroid? You should do the following. You should do x centroid times total area. What is the total area in this example? It's A1 plus A2 equals to, now for each figure, for each geometry, I find x of its centroid. You know that for a rectangle, the centroid is at the center. Okay? So let's say if this is my origin O, if this is my origin and this is x-axis, okay? This is x-axis. The centroid and the length of my rectangle is L. So here if I have the distance here is L. Okay? What will be the position of the centroid for the rectangle? It is L over 2. Okay? So from here to here, the distance is L over 2. And for a triangle, if you know the geometrical property for a triangle, you have the distance from this point to the centroid equal to 2L over 3. Because it's at 1 over 3 from the base, the centroid, and at 2 over 3 from the edge here. So you have 2L over 3. So if you want to find the centroid for this geometry, you will do x centroid times total area equals to x1, which is for the rectangle, yani L over 2, L over 2 times area rectangle, area 1, which is the area of the rectangle, plus 2L over 3 times the area of the triangle. Okay? This is how we calculate in math the centroid of an area. So here, because it's not simple geometry, because we have a function, we should find, instead of doing summation of xiai, we should do integration. So we can say that integral x dA over a is nothing than the position of the centroid of the area. So as a result, we can conclude from this slide that if we have a distributed load and we want to replace it by one force, the resultant force will be equal to the area under the curve, and the location of the force, it should pass by the centroid of the area. Okay? So here, for example, when you do integral x dA over integral dA, you will find the position of centroid of this area. So you get a certain value of x. This corresponds, this is x of the centroid. You calculate it by integral x dA over the area. And once you find it, you can say that I can replace my system by only one force passing by this point. And my force, F resultant, should be in magnitude equal to the area under the curve. This is the area I am talking about. The area between the curve and the x-axis. Okay? Now, we will do examples on this to understand it better. But do you have any question before we do the example?
Doctor, I
Yes.
didn't understand it. X bar. ما بعرف
Okay. You know, in math, you know how to calculate the position of the centroid of an area? What is the formula to find the centroid? Do you know it?
Yes, doctor.
Okay. What do you do to find the centroid of an area? What is the formula? Do you hear me? Okay, so I will repeat. If you want to find the centroid of an area, what you should do is the following. If you have here a function, an arbitrary function, okay, then you can say, if I want to find the location of the center of this area, I should do this. The formula is the following. X of the centroid times total A, okay, is equal to integral of x dA. Integral of x dA. Okay? Guys, let me try to okay. So I have integral x dA. Here in this problem, when we did the expression of the location, we obtained that distance d is equal to integral x dA over a. So we can say here that the distance d of point of application should be equal to, in my problem, I demonstrated that d is equal to integral x dA over a, okay? But if I look at the expression of the centroid from the mass relation for centroid, if I do integral x dA over a, what do I get? I get the position of my centroid. So from my formula, from the formula here, I obtained the distance d. I said that d should be in a way that the moment of F about O is equal to the moment of the distributed load about O. Okay? And when I wrote the condition of equal moment, I obtained that the distance d between F and O should be equal to integral x dA over A. But if I compare with the equation in mass of the centroid position, I can say that the distance here to the origin is equivalent to the position of the centroid. So I can conclude, when I have a distributed load, I can replace it by 1/4 equal to the area under the curve, because the equivalent force was found to be integral dA, which is the total area. And concerning the point of application, in order to have equivalent moment, the force should pass by the centroid, because when I found d from the origin, I found that d is equal to integral x dA over a, which is compatible with the definition of centroid position for an area. Okay? Let us do an example so you understand the idea better. In this example, okay, you have a nice house is sitting on the top of the ice and the wind. And the wind is hitting it at a speed of 40 miles per hour. The wind load is approximated by the distributed load shown in the figure. Calculate the total force that the wind exerts on the ice house and the point of application of the equivalent force. Okay, so for example here, in this problem, we have a house subjected to wind action. And they gave us that the distributed load of wind can be divided into two parts, as you can see in the figure. You have first a linear distributed load, and then after a certain height, you have a constant distributed load. Okay? And what you want to do, you want to reduce the system to only one force. Okay? To do this, you can see from your figures that this distributed load can be divided into two main parts. The first part is here, is a rectangular load, okay? And I will call it part 1.
Doctor, distributed load here, force of the wind.
Yes. And the second part is the triangular load, okay? So now, in order to reduce my system to only one force, I should work in steps. The first step, I can replace the rectangular distributed load by one force. The second step, I replace the triangular load by one force. And finally, I can reduce the two forces to only one force. So let us work step by step. If I start with the rectangular load, if I go back to my previous slide, to reduce it to one force, what is the condition? First, the force, the resultant force, should pass by the centroid of the rectangle. And you know that the centroid of the rectangle is here at the middle. Okay? So this is the centroid of my rectangle. This is why I can say that the resultant force that will replace the rectangle should pass by its centroid. Okay? And in this case, I know the centroid because for a rectangle, I know that it's a halfway. So here, the distance from here to here is, the distance is given here to be 4 feet. Okay? So I know that this distance is 4 feet. So the distance from the centroid and this one here is 4 also. Okay? And here the distance is also 4. So I can say that my centroid is at 2 meters from the top. So the distance from here to here, from the top, the centroid is at 2 meters. And from the bottom, it is at 6 feet. Okay? So this distance from the bottom to the centroid is 4 plus 2. So here it's 2. And here it is 4 plus 2 equal to 6. Okay? So now I know the location of the force that will replace the rectangular load. Now what about the resultant? This resultant force that is replacing the rectangular load should be equal to the area of the rectangle. What is the area of the rectangle here? I multiply W by the length of the rectangle. So I have W because W, if you want, is represents the width here, the width of the rectangle. It's 40 lb per feet. When I multiply by the length, which is 4 feet, I can get the magnitude of F resultant. So I can say here that F resultant 1 is equal to the area 1. Okay, area 1 equals to what? Equals to, I will write it here, FR1 equal A1 equals to 40 times 4. Okay, since your load is an lb per feet and the length is in feet, when you multiply, you get the result in feet. So your resultant force is 160 feet. Okay. Now, I am done with the first part.
Doctor,
Now, yes.
it's feet or pound? LB.
Sorry, LB, I mean, yes, it's LB. LB over feet times feet, it's LB, sorry. So
Yes.
here, 160 LB, okay? Now, the second step is to do the same work for the triangular load, okay? So I will just erase for more clarity. For the triangular load, I have here a linear distribution, which will lead to a triangular area. So first, I say that the resultant force replacing the triangle should be equal in value, in magnitude, to the area of the triangle. Okay? So F resultant 2 should be equal to area 2, which is the area of the triangle. How to calculate the area of the triangle? I have the width here. The width here is equal to what? Is equal also to 40 lb feet. The length here is equal to 4 feet. Okay? So now I can say that A2, I can calculate A2. A2 is equal to 40 times 4 over 2. Okay? Because for a triangle, it's base times height over 2. It's equal to 80 lb. Okay? Now, concerning the point of application, for a triangle, what is the location of the centroid? You have that the centroid is at 1/3 L from the base. So from here to here, you have 1 over 3 L. And from this point to the centroid, you have 2 over 3 L. So you can say that the distance from the bottom is 2/3 times L equals to 2/3 times 4. Okay, so it's equal to 8/3. So what we did until now, we have replaced our system by only two forces. Okay, so if I do a small figure here, what I did until now, I calculated the rectangular force. So this is F uniforms, I call it. This is F resultant 1. Okay, and for the triangular force, I calculated F resultant 2, and I determined the location of the two forces. What is the next step? The next step is that I want to reduce my distributed load to only one force, So I go back to the concept. If I want to reduce to one force, what is the condition? I should have same resultant force, same moment about any point. So first, to find the resultant force F resultant is the summation of FR1 plus FR2. Okay, so I already found that FR1 is 160 and FR2 is 80. So in total, my resultant force equivalent to the system is equal to 240 lb. Now, what about the location of F equivalent? So I still need to find where is the point of application of F equivalent. So I will find it here from the bottom. I will find what is the distance here from O to F equivalent, and I call this distance Y. I want to find Y. In order to find Y, I should apply the condition of equal moment, okay? Because we know that if I want to replace these two forces by one force, it should produce the same moment about O. Now I will write this equation. So my condition is that moment of F resultant about O, okay, should be equal to the total moment of FR1 and FR2 about O. So it should be equal to the moment of FR1 about O plus the moment of FR2 about O. Okay, so I have this is equal to, for FR1 it is 160, I replace it by 160, and we have calculated the distance from O, which is 6, so it's 160 times 6 plus, for the triangular load it's 80 lb, so it's 80 times the distance, which was 8/3. 8/3 is 2.67 equals to the moment of F resultant about O. What is the moment of F resultant about O? It's Y times F resultant. So it's 240 times the distance Y. The only unknown in this equation is Y. So you can calculate Y. Okay? So from the equal resulting moment, we can get the location Y. And in this way, we have replaced the distributed load in this problem to only one force, which is F equivalent, equal to the summation of FR1 plus FR2, and it should be located at a distance of 4.85 feet from O to produce the same moment.
Please, can
Any
you repeat
question?
FR1 FR2 over
Can I repeat for
about
what?
O? Give جبنا المومنت FR1
Okay.
FR2 about O.
I want, my purpose here is to replace these two forces by one force. Okay? So if I want to replace two forces by one force, what should I do? I should meet two conditions. First, I should have the equivalent force here is the summation of the two. Okay? So if this force here is 160 and this force is 80, the equivalent force should be equal to their summation equal to 240. The next step is to determine the point of application of F resultant. So what is the distance? I should find what is the distance between O and F result. This distance, I call it Y. Okay? In order to find Y, you should apply the second condition, which is that the moment of this force about O should be equal to the total moment of the other forces about O. How you calculate the moment of F equivalent about O? What should you do? You multiply the distance by the force. Okay? So you can say here that the moment of F equivalent is 240 times Y. So if I write it here, the moment of F equivalent to the system about O is equal to 240 times the distance to O, the projection from O to F. The projection distance is Y, so times Y. But this should be equal to what? This should be equal to the total moment about O, M resultant about O, okay? What is the resulting moment about O? You have two forces in this problem. You have the triangular force and you have the rectangular force. You want to find the total moment of these two forces. So it's equal to the force of the triangle is 80 lb. What is the distance of this force to O? It's 2.7 to 2.67. So to find the moment of F triangular about O, you do 80 times this distance, which is 2.65. So it's 80 times 2.67, sorry. Okay, plus what? Plus the moment of the second force, which is 160 times the distance from 160 to O. The distance from 160 to O is equal to 6. So you multiply by 6. So in this equation, your only unknown is Y, which is the distance between the resultant force and O. And when you solve, you can get Y. In this way, you can replace the two forces by only one force, which is equal to their summation and which is producing the same total moment about O. Okay? Any other question? If you have any question for the exam, I can open office hours whenever you want. So if you have questions for the exam, just tell me and we do office hours. I can open Zoom.
Doctor,
Yes.
for the exam, if the power cuts off, what do we do?